Hello everyone! Today I want to tell you about Krein-Milman theorem. It states that a compact convex subset of a Hausdorff locally convex topological vector space is equal to the closed convex hull of its extreme points. So let's define extreme points. Assume that we have a vector space X and a convex subset of X, K. K is a convex subset of X. And let's take a point A from K. We say that A is extreme point if from representation A is equal to tx1 plus 1 minus t x2 for t is greater than 0 and x1 x2 from K, it follows that A is equal to x1 is equal to x2. So let's now use some other forms of this definition and our first lemma. We say that if A from K and K is a subset, a convex subset of X, then the following are equivalent. So first, A is extreme point, and we will define extreme points as a X K. It's equivalent to if x1, x2 from K, and A can be represented as 1 over 2 x1 plus x2, then x1 is equal to x2 is equal to A. Third, that if we have n points x1, xn from K, and A belongs to convex of x1, xn, then A is equal to xi for some I from 1 to n. And the fourth, that the K without A is a convex. So I won't prove this equivalence, but if you want to, you can ask me and I will shoot a new video. So now let's try to prove the theorem. So our theorem. X is a locally convex space. Locally convex space. And K, it's not empty convex subspace of X. Not empty. Not empty compact. Not empty compact. Convex subset of X. Then K is equal to convex closure of extreme points of K. So, okay, let's prove it. First, consider the class U. It's a class of all not equal to K open subsets, all open convex subsets in K. It's a, well, let's write it. It's a class of all open convex subsets of K and it's not equal to K. Not equal to K. And we want to use a Zorn lemma to find the maximum element of our class U. And for that, we need to show that the condition for Zorn lemma is right. So let's consider a chain U0, U0 chain, and let's take a new set V0, which is equal to union of all UI with UI from U0, and it's open convex space. It contains all of UI, and we now need to show that it's not equal to K. So let's show that V0 is not equal to K. So let's assume contradiction. And then sets from U0 cover our space K, but our space K is compact, so we can say that K is equal to union of UI. K is compact, therefore K is equal to finite union of our sets from how to write it correctly. Let's write it like that. And since our sets lies in each other, since it's a chain, so it follows that K is equal to sum over set UG. But it's a contradiction because UJ is not equal to K. So let's define set W as a maximum element of our class U. So maximum element of class U. And now I want to show that K without W consists of one point. So let's do it. Let's first define a function t, which depends on x and lambda, and which is a function from k to k, where x belongs to k and lambda is from 0 to 1. Well, we will define this function as follow. And now I want to show some good properties of this function. Let's first see the continuous function, and it's obvious from our definition of function. Now let's take coefficients ai such that they sum equal to 1. The sum of from 1 to n ai is equal to 1. And I want to consider a point which is equal to the sum of ai times y, where y is from our set k, and it lies in k since k is convex, and it's equal to just the sum of coefficients ai times tx lambda y. So the next step is, let's consider our point x from w, and it can be seen that tx lambda map our set w inside our set w, since it's a convex sets. And now we can say that w is a subset of tx lambda. It's of w. It's an image of our open set, so it's a open convex subspace of K. So third step, let's take a point y from closure w without w, and I want to say that tx lambda of w belongs to the set w. Tx lambda of y belongs to w. So we can say that closure of w is a subset of the pre-image of w, and from that we can get that pre-image of w is equal to k, since our set w is a maximum element which is not equal to k, so therefore the pre-image has to be equal to k. And from that we also get that tx lambda of k is a subset of w for all x in w and lambda less or equal than 0, greater or equal than 0 and less than 1. And now I want to show that if we have a open convex subset of K, open convex subset of K, then union of V and W is equal to either W or OK. So let's first show that it's a convex subset. So let's assume that it's wrong, and we want to show that the union is convex and assume a contradiction. Then we have 2 points from our union such that there exists a lambda. Ooh. Such that lambda x plus 1 minus lambda y doesn't lie in our union. Without loss of generality, we can say that x from W, and then our mapping has to lie in W, but from our assuming we get that it doesn't lie in W, so it's a contradiction. Therefore our set is convex. So now let's assume the cardinality of K without W is greater than 1. Let's assume it. Why it doesn't work? Assume. Then we can find at least 2 points A and B from K without W, and find 2 neighborhoods of these points, VA and VW neighborhoods, such that they don't intersect. And it can be seen from our steps before that VA union with W has to be equal to K, but our point B doesn't lie in VA, so it has to lie in our set W, but it's a contradiction. So we get that the cardinality of K without W is equal to 1. And I want to step a little bit outside of our theorem now and show example of what we just proved. So assumed you have a disk, it's a K with a border. Well, it's a compact convex subspace of R2 of our plane, and if I ask you what's the biggest subset of our set K which is convex and open in K, then it will be our disk without 1 point. So it will be our disk without 1 point. So it will be W, because we just shown that K without W, the cardinality is equal to 1. So it's just a cool example of what we have done. So next step, it will be a small lemma number 2, that if F is a open convex subset of X, and the extreme points of K lies in V, then our set K lies in V. So the proof. Let's assume that it's not correct. Then we intersect with K is not equal to K. Therefore, there lies in our class U, which we defined on our step 1. It belongs to U. Therefore, there exists a maximum element Q, which can be equal to W, such that we intersect K lies in Q. However, we have shown that the cardinality of K without Q is equal to 1, so there is one point such that K without Q is equal to this point. And from that, we can say that K without this point is equal to Q, and Q is a convex, and from our equivalence of extreme points, we can say that A is extreme point. A is extreme point of K. But that's a contradiction, because A doesn't belongs in V. So we just prove our lemma. And well, now we can finish our theorem. Let's define a set E which is equal to convex closure of extreme points K. It can be easily shown that A is a subset of E is a subset of K, and assume that there exists a point such that well, let's assume that E is not equal to K, so there exists point B such that B lies in K and B doesn't lie in E. And since our space X is locally convex, we can separate our set E from the point B, so we can find such functional y and coefficient alpha such that E is a subset well, we just well, let's write it a little bit correctly. So we just separated our set E from point B, and we define this set as a set V. Since our space E lies in V, then from the lemma number 2, it follows that K lies in V. But then K without V is not equal to 0, so it's a contradiction, and K is equal to E. So we just proved Krein-Milman theorem. Thank you very much.